Here's lesson B of Unit 2, Newton's second law, and our targets here are to be able to understand that acceleration is directly proportional to net force and indirectly proportional to mass. Understand that static friction keeps objects in place and kinetic friction is sliding friction, and understand the difference between mass and weight. So in this lesson we're going to be focusing on things that affect acceleration and friction and mass and weight. So to start thinking about forces, let's think first about this situation here where we've got these guys pushing on this car. So they apply a force and the car begins to move. It begins to accelerate. And these folks are able to get a pretty decent acceleration out of it because there's 3 people in there. So, but what if, let's imagine for a moment that 2 of these people are no longer there and there's just 1 person pushing. Are they going to be able to get the same acceleration out of the car? Well, your experience would tell you, no, of course not. They're not going to get the same acceleration out of the car. So remember from lesson A that the combination of forces acting on the object is what we call the net force. And acceleration depends on the net force. To increase the acceleration of an object, we have to increase the net force acting on it. If I double the net force on an object, its acceleration doubles. If I triple the net force, its acceleration triples, and so on. And this makes good sense. We say that an object's acceleration then is directly proportional to the net force acting on it. That's what this little symbol right here means. This is an alpha, and it means directly proportional. And it means that any change in one is the same amount of change in the other. So as I double the net force, I will double my acceleration. So let's think about pushing a crate on a smooth floor. So if I push on this crate and it accelerates, if I apply, say, 4 times the net force on this, how much greater will be the acceleration? Well, the acceleration is going to be 4 times greater. Now, let's say I push with the same increased force on the same crate, but it slides on a very rough floor instead of a smooth floor. In that case, then how will the acceleration compare with the crate being pushed on the smooth floor? Well, because we're pushing on a rough floor instead of a smooth floor, it's going to have less acceleration than it did on that smooth floor because of friction would reduce that net force. So now let's move on and talk about friction. So when surfaces slide or tend to slide over one another, a force of friction acts. And the effect of friction is to reduce the net force. If you were to push something across ice versus push something across gravel, you're going to get a lot more friction out of the gravel than you will the ice. So friction is caused by irregularities in surfaces that are in contact, and it depends on the kinds of materials and how much they're pushed together. See, even surfaces that appear to be really smooth have microscopic irregularities that obstruct motion. The atoms cling together at many different points of contact, like here. So when one object slides against another, it has to either rise over the little irregular bumps or scrape atoms off of each other. Also, it's important to realize that the direction of friction force is always in a direction that opposes the direction of motion. So if I'm pushing a box across the floor this way, friction will always oppose that motion. If I take that box and I tilt it so it's on a ramp, that friction force is going to point down the ramp. So if an object is to move at a constant velocity, then a force equal to the opposing force of friction must be applied to that object so that the 2 forces cancel each other out. Then the net force ends up being 0 and we have 0 acceleration and constant velocity. Now, no friction exists on an object that just sits at rest somewhere on a level floor, but if you push the crate horizontally, you'll disturb the contact surfaces and friction is produced. So before pushing, no friction exists. Once pushing starts, friction is produced. But the question is, how much friction is produced? Well, as long as the crate's at rest, enough friction is produced in order to keep that object at rest. And we've all experienced this. I mean, we've all pushed on something, and as long as we can push, and then it begins to move. Let's think about for a moment that point where it just begins to move. If I'm pushing on an object and I push for a time, and then it gets to a point, it's like it slips, and then it starts moving at a constant speed. Well, let's think about that slip for a minute. As I'm pushing on it and it's not moving, as that static friction exactly matches my push, okay? And that increases to a point where then that object slips and begins to slide. So if I'm applying a force of, say, 30 newtons, okay, I'm going to get a static friction force of exactly 30 newtons. But at some point, I apply enough force to cause that thing to begin to move. Okay, so I overcome that friction force. So there's two types of friction that we talk about. There's static friction and kinetic friction. Okay, static friction is that type of friction that keeps an object from moving. Okay, so when I'm pushing an object and I push, static friction is what keeps that object from moving. When I suddenly get that slip and I lurch forward and then I begin to be able to slide that object, that sliding friction is called kinetic friction. Okay? So it's interesting to see from this graph here that my static friction matches my applied force all the way up to that threshold point. And then my kinetic friction, or that sliding friction, is less than that static friction. So I can exert 40 newtons of force, I get 40 newtons of friction. If I exert 50 newtons of force, I get 50 newtons of friction. But when I exert 60 newtons of force, I get 40 newtons of friction. So my kinetic friction drops lower than my static friction, and it stays constant. And so even as I push harder, at say 80 newtons of force, I'm still getting the same 40 newtons of friction. So it's really interesting that this friction force, the kinetic friction, does not depend on the speed at which the object's moving. A car skidding at low speed has about the same friction as the same car skidding at a high speed. Also, friction does not depend on the area of contact. If I slide, say, a rectangular brick on its flat, wide side, I'm going to get the same amount of friction as if I slide it on its narrow side. And when I turn it on its narrow side, all I'm doing is concentrating the same weight in a smaller area, with the result that the friction is the same. So those really extra wide tires that you see on some cars provide no more friction than the more narrow tires. The wider tires simply spreads the weight of the car over more surface area to reduce heating and wear. And in the same way, the friction between like a truck and the ground is the same whether the truck has 4 tires or 18 tires. All the additional tires do is spread the load over more ground area and reduces the pressure per tire. We also want to recognize that friction is not restricted to just solid objects. It also affects liquids and gases. Liquids and gases we call fluids. And one of the real common types of fluid friction is air resistance or air drag. So the acceleration that's imparted to an object depends not only on the applied forces and friction forces, but the inertia of the object. How much inertia an object possesses depends on the amount of matter in the object. The more matter, the more inertia. In speaking of how much matter something has, we use the term mass. The greater the mass of an object, the greater its inertia. So mass is a measure of the inertia of a material object. So mass corresponds to our intuitive notion of weight. We casually say that something has a lot of matter if it weighs a lot, but there's a difference between mass and weight. Mass is the quantity of matter in an object. It's also the measure of inertia of the object, or the sluggishness that an object exhibits in response to any effort to make it start moving, stop moving, or change directions. Weight is the force upon an object due to gravity. So we get an object's weight from the force of gravity pulling on that object. So imagine you've got an anvil out in space, a big metal block, basically, out in space, it's not going to have much weight because there's not Earth pulling down on it as much, but it will have the same amount of mass that it would have on Earth, okay? Because it's still the same amount of matter, still has the same inertia. So in that kind of situation, if you were in space and you had two objects and they were identical but had different masses, in order to figure out how much mass they have, one way to figure that out would be to shake the objects. The object that resists the change in motion of shaking is the object that has the greater mass because it has a greater inertia. So when we go to measure mass and weight, we always measure mass in kilograms and we'll always measure weight in newtons. Okay, so weight is a force, mass is not a force. So if you were to push on a bulldog on a skateboard, you'd be able to get a pretty decent acceleration out of it. Imagine, though, pushing with the same force on an elephant on that skateboard. Would you be able to get the same acceleration out of it? Clearly, no, you're not going to get the same acceleration out of the same force off of that elephant. What this shows us is that acceleration, while it's directly proportional to net force, it is indirectly proportional to mass. As I increase the mass of an object with the same amount of force, I'm going to decrease the acceleration. So these two relationships that we've looked at, that acceleration is indirectly proportional to the mass and that acceleration is directly proportional to net force, we know as Newton's second law. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on the object. It's in the same direction as the net force and is inversely proportional to the mass of the object. So to summarize Newton's second law and put it into its briefest form, we were going to say that acceleration is equal to the net force over the mass. An object is always accelerated in the direction of the force acting on it. Applied in the direction of the object's motion, a force will increase the object's speed. Applied in the opposite direction, it's going to decrease the speed. Applied at right angles, it will deflect the object, make it change directions. Any other direction of application will result in a combination of speed change and direction change. The acceleration of an object is always in the direction of the net force. Okay, so let's take the example of falling objects. Objects can fall in kind of two ways, in what we call free fall and non-free fall. When objects are falling under only the influence of the Earth's gravitational pull, we say that they're in free fall. In those cases, the acceleration is a rate of what we call g, 9.8 meters per second squared. Now, it does not mean that a more massive object is going to accelerate greater than a less massive object. An object that is more massive will just get pulled down by the Earth harder. Kind of take this idea and maybe turn it on its side, right? So if you were out in the parking lot and you have a small car and a large truck, and you wanted to accelerate the small car and the large truck at the same rate, which one would you have to push harder on? Well, you have to push harder on the large truck because it's more massive. The same is true for the Earth in falling situations. In order to accelerate this larger object at the same rate of acceleration as the small object, Earth has to pull harder on the large object than it does on the small object. Okay, so now let's take an example of cases where things are falling under not only the force of gravity. Okay, so if we have an upward drag force from like a parachute, we have non-free fall. Okay, and in those cases your acceleration is going to be less than g. When we have upward forces of air resistance, we end up getting to a point where the object can no longer accelerate anymore, and we reach what's called terminal velocity. Okay, even the rocks over here, given enough space, given enough height, will eventually reach a terminal velocity. But under short distances, they're air resistance is very, very small and can be ignored. But in a case like parachutist, or maybe dropping paper onto the floor, the air resistance is quite high, and eventually the object will reach a terminal velocity and no longer accelerate. Now, that's not to say that you get to a certain point and then suddenly stop accelerating. It's not that this parachutist will accelerate at 9.8 until they reach terminal velocity and then go to 0. As the parachutist falls, acceleration decreases because the net force on the parachutist decreases. Okay, so it takes place over time, not an instantaneous thing. All right, so that'll end the video for lesson B here. Make sure you go through the reading and pay attention to the check yourself questions as we go through them. See you in class.